Hey, it's Plumber Tom. Don't forget to check in the comments below for a link where you can find additional resources like practice tests and courses that you can take. Your support helps me to be able to create more great content. Thanks for watching. Hello, welcome to this presentation of the International Fuel Gas Code. My name is Thomas, and in this presentation we are continuing our examination of gas pipe sizing. This is section 402 from chapter 4 of the International Fuel Gas Code. In another presentation, I've already examined the section 402 and talked about what's in that, how we go about sizing, the different methods that are available, and we did one example. If you haven't seen that presentation, make sure that you watch that first. This one will make more sense if you have watched that. Okay, we're going to do another example of the longest length method in this presentation. So make sure you get your books, follow along. Let's get to it. So here we are, gas pipe sizing, section 402. Let's review a couple of key concepts before we jump in and start sizing another diagram. First of all, remember 402.1, we have to provide sufficient gas for the maximum demand and not less than the minimum supply pressure. That means we make sure there's enough gas available for all appliances connected if they're all running at the same time at maximum capacity. That's what we have to provide. Inadequate supply pressure can result in hazardous appliance operation or malfunction. We do not want the danger involved with poor operation of a fuel gas appliance. You don't want to be responsible for that. Let's jump into the sizing methods. There are 3 presented in the text of the code. We are going to use pipe sizing tables because it's the most basic, straightforward way to get around this. So there's a whole bunch of tables. You flip through this if you haven't already. Go through section 402 and you will find a lot of tables. You'll need to make sure that you know which table to use depending on the system that you're installing. And I explained that in the previous video. We'll review that briefly here. But one other reminder, each appliance is going to have a maximum BTU value. That's what it's requiring at its max. And each cubic foot of gas is going to be able to burn a certain number of BTUs. At sea level, 1 cubic foot of gas can produce 1,000 BTUs of energy. And that's our baseline. That's what we're going to use for this. It really simplifies our math when we're doing sizing. We'll take the maximum BTUs, in this example 120,000 BTUs per hour for a given appliance. Divide that by the number of BTUs available in 1 cubic foot of gas. That's 1,000, and we get 120 cubic feet per hour. That's the requirement that that appliance will need in order to function for 1 solid hour at maximum capacity. 120 cubic feet per hour. Again, this is at sea level, and it simplifies. We can just remove the 3 zeros off our hundreds of thousands or tens of thousands and run with our cubic feet per hour. Now, if you're at a higher elevation, please remember that you have to derate for that elevation. You cannot use these same numbers and assume that you're going to get 1,000 BTUs for 1 cubic foot of gas if you're at 4,000 feet above sea level. You cannot do it. I will show you how to go through that duration in another video, but for now, let's move on. We're going to be using the longest length method. In this method, the size is determined using the longest length of piping from the point of delivery to the most remote outlet. And let me point out, this is the best and simplest of all forms or methods of sizing. So if you want to make sure you get it right and that you're never undersized, go with the longest length method. You'll be great. Here is the commercial gas system we're going to look at. In the last video, we looked at a residential system. This one is a commercial system. That means it's got larger appliances. All of these are RTU. We have RTU1 at 150,000 BTU, RTU2 at 90,000 BTU, RTU3 at 200,000 BTU, RTU4 at 100,000 BTU, and RTU5 at 150,000 BTU. If you're wondering what RTU stands for,
hello, I am RTU3 Special Space Restroom Custodian at your service.
let me just tell you, it's rooftop unit. That's what we're talking about. We've got a bunch of rooftop units that produce heat and push it down into the ductwork and heat this commercial building. That's what this whole system is about. All right, other important things to note about this system. It has an inlet pressure of 8-inch water column. We are using Schedule 40 steel pipe. It is a natural gas system with a specific gravity of 0.60. And you'll note on this illustration that we do have pipe sections indicated by letters A, B, C, D, and so forth, as well as the length from one point to another. That's going to allow us to work through the sizing of this system. Quick review of the steps for the longest length method. These are not listed out in the code book in this order, but this is, I feel, a pretty good way to take this process step by step. First of all, we need to go find the maximum BTU per hour for all of the appliances. Second, we'll find the section pipe lengths. Third, we need to find the developed length for the system. That's the furthest distance from start to finish, from the point of delivery to the last and most furthest appliance. That's our developed length. We will then calculate the cubic feet per hour for all of those sections of pipe, and then we will select the correct sizing table, making sure that we're using that table that will apply to the system we have. And finally, we will use the table to size the pipe sections. Here we go. As we looked at that diagram, we found that there were rooftop units. If we list those out, we have RTU1 at 150,000 BTUs per hour, RTU2 at 90,000 BTUs per hour, RTU3 at 200,000 BTUs per hour, RTU4 at 100,000 BTUs per hour, and RTU5 at 150,000 BTUs per hour. Remember, we're going to put this on a table, and I'm going to expand this table. It's going to be pretty big by the time we're done. This is just the beginning, and when you're sizing, we want to make sure that you have things laid out on a table or very well illustrated on a diagram so that all of your information is accurate, visible, and you can make sure you stay on track and that you're correct. Here's the second step. Find the section lengths of the pipe. It's a really good idea to draw the system out. Now, I do my best to get it to kind of to scale, but it's not to scale. I mean, really. Sometimes just to make things fit on the paper, we scrunch up a little bit. But this gives us a visual for the whole system. This step 2 involves finding the section lengths for each. So in order to do that, we have to assign some way to organize this, right? That's why we put A, B, C, D, and so forth on each section or branch headed to one of the rooftop units so that we can size those individually based on the number of cubic feet per hour that is either going to the branch or that is being carried on the hole, on the main line. So we have all of those sectioned out. That's why we have these labeled with letters. Now, if we want to find the developed length, and that's going to be the next step here, we go from the source or the point of delivery, that's the meter, all the way to the furthest unit. Now, if I trace that through, following the pipe, through bends and other things, you can see the red line here is taking me from the meter to rooftop unit 5. I can go through because I know each of those lengths between and add those up. If you'll notice, we have 50 feet on A, plus 10 feet on B, plus 30 feet on C, plus 70 feet on D, and then let's follow that down. We've got I is another 50 feet. The total developed length for this system is 210 feet. That's the number we're going to hold on to throughout this sizing exercise. It's 210 feet. Now we'll get into number 3. We're going to calculate the cubic feet per hour for all of the pipe sections and appliances. This is where it's useful to take what we see and put it all onto a larger table where we can spell out all of the sections, all of the BTUs, all of the cubic feet per hour, and find our sizes. Here we go. Section A. On Section A, we're carrying the full load of the whole system. So if we go through and add up all of the BTU requirements for all of the rooftop units, we're going to find that we have 690,000 BTUs. We divide that by our BTU per cubic foot at 1,000. Remember, we're dividing here at sea level, and we'll get 690 cubic feet per hour. That's the number we need in order to size on our tables. We're going to do that same thing for every section. Let's do it quick. Section B. If we look at B, now it's gone past rooftop unit 1. That means we can subtract off 150,000 BTUs. B is still one of those main lines. It's going to have things branching off of it, but it's not carrying as much as A was because A has everything, right? All the BTUs. So on B, we have 540,000 BTUs. We divide that by 1,000 and we'll get 540 cubic feet per hour, and we're ready to size that section. Go to section C. Once we get to C, rooftop unit 2 has now branched off and it's not carrying those BTUs anymore. So now C is just carrying the BTUs for rooftop unit 3, 4, and 5. That said, the total BTUs for those rooftop units is 450,000 BTUs on section C. We divide by 1,000 and we get 450 cubic feet per hour. Let's go to section D. D is the last section that is carrying more than one rooftop unit. Everything else is a branch. So D is carrying all of the BTUs for rooftop unit 4 and rooftop unit 5. The total for that is 250,000 BTUs. We divide by 1,000 and get 250 cubic feet per hour. You see how this goes. The rest of these are all just the rooftop unit connections. We're going to take each of those and divide them by 1,000 to get our cubic feet per hour. So E, rooftop unit 1, had 150,000 BTUs. Divide by 1,000, we get 150 cubic feet per hour. F is rooftop unit 2. It's got 90,000 BTUs. We divide by 1,000 and we get 90 cubic feet per hour. G, rooftop unit 3, it has 200,000 BTUs. We divide by 1,000 and we get 200 cubic feet per hour. H, rooftop unit 4, we have 100,000 BTUs. We divide by 1,000 and we get 100 cubic feet per hour. And finally, I, rooftop unit 5, we have 150,000 BTUs. Divide by 1,000 and we get 150 cubic feet per hour. Our table is complete to this point. We have our developed length is 210 feet. We have all of our cubic feet per hour for every section and every branch of this system figured out. At this point, we can select our sizing table and then go to work sizing each section and branch of pipe. Now, please remember when you're finding the table, you're looking for several things. First, what type of pipe is being used on this system? We know that this is a Schedule 40 metallic steel pipe, so that's going to narrow down some of those tables, but there's quite a few of those. The next thing we look at is the type of gas, the pressure of gas, and all of that. If you remember on our system, we had 8-inch water column, Schedule 40 steel, natural gas, and specific gravity of 0.60. As we look at all of those requirements for this system, it's going to narrow it down to table 402.4, parentheses 2, and that's the one that gives us Schedule 40 metallic pipe for the right range of gas. Once we've selected that table, we can use the table to size the specific sections. Remember, you go to the left column with your developed length. In this case, our longest length was 210 feet. Then we come across on that row with the cubic feet per hour for whatever section we're sizing, and then we go up to the top and find our gas pipe size. All right, here we go, ready to size this out. We've got our whole table. Let's start with section A. It's the big one. It's carrying everything, the full load. We've got 690,000 BTUs. Let's take that to the table. Remember, we've got to go down on those rows with our 210 developed length. If we come to the bottom here, we've got a row that's 200 and then another row that's 250. We always have to go greater than or equal to. So we're going to use row 250 for all the pipes we're going to size in this system. As we go to this row, and we have 690. We come across from left to right. It's more than 30. It's more than 63. It's more than 119. It's more than 244. It's more than 366. And it's finally less than 704. We're into a column that it would fit. Or we're into a pipe size that can handle all those cubic feet per hour. Let's go up to the top, and we find that it's going to need to be a 2-inch pipe. So we put that on our table. Section A, 2-inch pipe. Let's go on to section B. For section B, we have 540 cubic feet per hour. If you remember section B, we've already branched off for rooftop unit number 1, and we're carrying the load for the rest. At 540 cubic feet per hour, we're going to stay on that 250 line. Coming across, again, it's more than 366. It's less than 704. So we go up to the top, and we're going to find that once again, we have 2-inch pipe. That means we're going to continue with 2-inch pipe through that next section. Let's go on to the next one. Pipe section C. We've dropped off another one of those rooftop units, rooftop unit 2. C is now carrying the load for your rooftop unit 3, 4, and 5, and the total cubic feet per hour on that is 450. So we take that 450, come across on that row, 250 was our developed length. It's more than 244. It's more than 366, but it's less than 704. So we're still in there at 2-inch pipe as we go up to the top there. 2-inch pipe all the way through section C. Let's go on to section D. Section D now has 250 cubic feet per hour. All it's carrying is rooftop unit 4 and rooftop unit 5. So it's 250 cubic feet per hour. As we take it across on our line 250 for our developed length, it's more than 119. It's more than 244, but it is less than 366. So we can stay in this column, go up to the top, and we find that we now have 1.5-inch pipe for section D. We'll put that on our table. We've got section D is 1.5-inch pipe.
All right, yeah, we got the main trunk line done. Woo-hoo-hoo, yeah!
From here, we're on to our rooftop units, and we can size out each of the branches individually. For section E, rooftop unit 1 has 150 cubic feet per hour. So we'll take it on that line, 250. We've got 150. It's more than 119. It's less than 244. We can stay in that column, go up to the top. We're going to have 1.25-inch pipe for that rooftop unit on the branch of E. Let's go to branch F. This time we have 90,000. We come across the bottom with our 90. We're on row 250. It's more than 63. It's less than 119. So I'm going to stay in that column, go to the top, and I find this is a 1-inch pipe. We can run a 1-inch pipe over to the rooftop unit number 2. All right, let's go on to G, rooftop unit 3. We've got 200,000 BTUs or 200 cubic feet per hour. We go to the table, drop down to line 250, coming across with the 200. It's more than 63. It's more than 119. It is less than 244. So we stay in that column, go to the top, and we find that we have a 1.25-inch pipe size for G. Let's go on to H, rooftop unit 4. H has 100,000 BTUs or 100 cubic feet per hour. So we come across on our line 250 with 100. It's more than 63. It's less than 119. We can go up to the top there and find we've got a 1-inch pipe. So we have 1-inch for rooftop unit 4. Finally, rooftop unit 5. Rooftop unit 5 is all the way out there at the end. It's got 150,000 BTUs or 150 cubic feet per hour. As we take that to our table on line 250, we've got 150. That's more than 63. That's more than 119. It's less than 244, so we can stay in that column, go to the top, and we find, once again, 1.25-inch pipe. We've done it. We have sized out all of the sections and branches on this system. And this gives us enough information to go order parts, right? I can order my pipe, my fittings. I can order the right tees as they're branching off. This is what I need in order to move forward.
All right, yeah, I'm so glad we're done with this sizing exercise. Woohoo, yeah!
Now let me remind you, if you've gone to all of this work to figure this out, you owe it to the end user, the owner, whoever is going to take care of that building later, to leave them with this information so that if they ever need to make changes, they have it. You might leave it in a table format like this, or you might leave them with your whole illustration and pipe sizes diagrammed on there. While we're looking at this diagram, I want to do something a little bit different just for comparison. Let's throw in something that we haven't looked at yet, and that is variable pressure. Look at the top here, inlet pressure of 2 psi. Let's say I bump it up from that 8-inch water column to 2 psi. Everything else is the same. We're using steel pipe, natural gas, specific gravity 0.6. We are going to use a different table because now we're at 2 psi. But let's see what happens to this whole system if I'm using high pressure. Watch the difference on the pipe sizes. Here we go. You've seen this table. We've already figured out all of the cubic feet per hour and our developed length. We can move forward with sizing. We're going to size out section A. It's got 690 cubic feet per hour. I am now on table 402.4 parentheses 5. And notice on here it's natural gas. 2 psi is our inlet pressure. We've got specific gravity 0.60. So this is the one I'm using for a higher pressure system. Watch what happens. I have the same developed length, 210. So we're going to come down here to line 250. I have 690 cubic feet per hour. Let's bring that across. It's more than 279. It's more than 583, but it's less than 1,040. So I found my column. I come to the top. I've got 1-inch pipe. Put that on my table, 1 inch. Let's go with the 540 on section B. I'm going down to line 250. 540 is more than 279. It's less than 583. I can stay in this column, go to the top, and I've got 3/4 inch pipe. I'll put that on my table. Look how much we're already going down. Okay, section C, 450 cubic feet per hour. Take it to my table. I'm on line 250 for my developed length, and I have 450. It's more than 279, but it's less than 583. Go to the top. I still have 3/4 inch pipe running along. Put that on my table. Section D. This time I have 250 cubic feet per hour. I'm on line 250 for my developed length. I come across. It's less than 279. I come to the top of that column and I find I've got a 1/2 inch pipe. I can put that on my table. Okay, we could sit here and size out all of these branches, but let me just point out they are all less than 250. So everything else in this system, every branch to the rooftop units is going to come out to be 1/2 inch. All of them. Look at the sizing difference here. This system is 2 psi. My biggest pipe is 1 inch. Everything else, 3/4 or 1/2. Most of it's 1/2. Let's compare that to what we had before. We had 8-inch water column. We had 2-inch pipe sizes for a majority of the main lines of the system. Then it goes to 1.5, 1.25. These are big pipes. We've got 1.5 going to some of the rooftop units, 1.25. The pipe size differences are amazingly different. And the point I'm making here is that if you're trying to save money on labor and materials and you're doing a big system, you'll always do better if you can increase the pressure, which automatically reduces the pipe sizes. Now, of course, at every unit, you're going to have a regulator that brings it from 2 psi down to our 4-ounce or that 8-inch water column, whatever's required at the units. But the point here is you can do a lot with higher pressure. It can save a lot of money. All right, there you have it. Our second example of longest length method for gas pipe sizing. I hope you found this useful. We looked at a commercial system and we compared 2 pressures. This is the process for longest length method. If you will do this for your sizing of any gas system, apply these steps, apply these principles, then you're going to do great. But this is not all. There are still several other methods that we will look at: the branch method, the hybrid method, and most definitely, if you are not at sea level, which a lot of us are not at sea level, you're going to have to do some deaeration. And that in gas pipe sizing is critical. So make sure you stay tuned, watch the other sizing videos so that you understand the differences and the options and how to do this correctly. Thank you for watching. I'll see you next time.